problem, we put or we assess only the value of objective function. We do not bother to compare the two solutions based on the constraint satisfaction, isn't? But in case of constraint optimization problem, comparison of two solutions should be based on both the criteria. How it is good for objective function and how it is good for satisfying constants. Both the criteria should be taken care by the algorithm while comparing two solutions to accept the better solution. Is it understood or not?
Yes, sir.
So the new requirement in the constraint optimization problem is to introduce certain criteria, certain logic, which can take care of the quality of the solution based on the constraint satisfaction, the feasibility of the solution. Because in the algorithm already the parameter, we know two solution based on the objective function. Now we have to learn, or rather we have to identify what can be the logic, what can be the technique by which we can assess the quality of the solution based on the constraint function also, feasibility of the solution also. It will be the new task for constraint optimization problem. Is it understood?
Yes, sir.
So if a question is given, compare unconstraint optimization problem and constraint optimization problem. Can you write it?
Yes, sir.
Distinguish between constraint and unconstraint. An unconstraint optimization algorithm cannot find out the constraint optimum solution. Explain. I think all these questions I have tried to make you understood. Is it clear to you or not?
Yes, sir.
Yes, sir.
So now, in the earlier case, we started before going to any algorithm. Here, again, I have tried to give you some difference between constraint and unconstraint optimization. Look, in the figure, a unimodal function is given where a minima lies between A and B. Okay. If the unconstraint optimization says that find out the minima of the function, you know this is the minima. The left figure, the minima is given, isn't? But if one constraint is attached that x must be less than equal to c, then this point is not a feasible solution. So it is not the constraint minima. Though it is minima within the given interval, but as because it is not feasible, as it is not satisfying the constraint, so it cannot be acceptable as constraint minima. Rather, if we draw a vertical line at C, it will cut the function at some point. That point is probably the constraint minima because it is satisfying the constraint as well as it is the minima among the points satisfying the constraint. Am I right or not?
Yes, sir.
So by this, though the example is very simple, but it is quite convenient for understanding the difference between a constraint and unconstrained minima. Is it clear?
Yes, sir.
In the case of unconstrained optima, within using some classical methods or principle, we can find out the optimal points by making gradient equal to 0 or checking criteria, certain criteria. Using the function and derivative information, we can find out the points where the minima or maxima can be, because all the points where gradient is equal to 0 are not minima and maxima. It may be a point of inflection. No, they are only stationary points. But all the stationary points are not the optimal points. I think it is already understood in case of unconstrained.
Yes, sir.
But in case of unconstrained, while finding or searching for the stationary points, we have taken that grad fx, where fx is the objective function, equating grad fx 0. We have tried to find out the stationary points. Then onwards, checking the value of the second order derivative at the point, we took decision that whether the point is minima, maxima, or point of inflection. Is the idea clear?
Yes, sir.
But if there are constraints, is there any technique by which we can identify stationary points? That means stationary point means that that can be a possible point for being optima. It may not be the optima, but there are possibility that at these points, minima or maxima can be there. In case of constraint problem, a Kuhn-Tucker criteria, it is called Kuhn-Tucker criteria or conditions for finding out stationary points. That means we can check other condition, whether first we have to find out the Kuhn-Tucker points. The points which satisfy the Kuhn-Tucker conditions are called Kuhn-Tucker points. And then after getting the Kuhn-Tucker points, at those points we have to check certain other conditions to take decision whether they are optimal or not. And here I have given the list of Kuhn-Tucker conditions. First of all, not only the grad fx, but we have to take care of the grad of the constraint functions. Okay. Suppose we have j number of unequal to constraints, that gjx greater than equal to 0. First of all, there are j number of inequation type constraint and k number of equal to constraints in the problem. So first condition for getting Kuhn-Tucker point is that grad fx minus summation of uj grad gjx. Uj grad gjx. U is some parameter or some constants taken for this problem. So it will be U1 grad GA1, U2 grad G2, U3 grad G3 in this way, and then minus summation of Vk grad Hkx equal to 0. So we have introduced J number of U parameter and K number of V parameter, and we have calculated the grad G and grad H and grad Fx, and then equating to 0. It is the first equation to be satisfied by the Kuhn-Tucker points. Is it understood?
Yes, sir.
Secondly, in the problem already given, two series of constants that Gjx greater than equal to 0, Hkx equal to 0. Fourth constant that Uj, Gj, we have to make 0 gradually. And all the Uj should be greater than equal to 0. If we solve, then we will get the value of Uj, and all the Uj, U value should be greater than equal to 0. When a point satisfies all these conditions, then the points are called Kuhn-Tucker points. And Kuhn-Tucker points are the possible points where constraint optima can lie. Is it understood or not?
Yes, sir.
So suppose in a problem, this is the objective function and these two constraints are given. That G1x greater than equal to 0, G2x greater than equal to 0, X1 greater than equal to 0, X2 greater than equal to 0. So actually there are 4 constraints. Is it understood? G1, G2, G3, G4. G3 means X1 greater than equal to 0 and G4 means X2 greater than equal to 0. So 4 inequation type constraints and the objective function. So we can calculate the grad fx and grad G1, etc. We can evaluate this G1, G2, G3, G4 grad. And now putting the value, these are the equations we obtain. Okay. Putting in the Kuhn-Tucker's condition, these are the equations obtained. From here, we can solve U1, U2, U3, U4. As because there is no equal to type constant, so there is no V in the problem, but in otherwise V can be present. Here all these points, all these equations contains only U1, U2, U3, U4. Is it clear or not?
Yes, sir.
And now, by solving this, we have got U1 0, U2 0, U3 minus 14 and U4 minus 22. So all these U are not greater than equal to 0. We have started with a solution because making the first equation, we have got several points, and at every point we have to check the value of U1, U2, U3, U4. At certain points, all the U cannot be positive. At certain point, all the U may be positive. The points where all the values of U are obtained as positive, those points are Kuhn-Tucker points. Is it understood? How we have to check for Kuhn-Tucker conditions?
Yes, sir.
Here the problem is given, detail. I think you have understood the principle of checking?
Yes, sir.
Okay. That is the classical method of checking the optimality condition for constant problem. But we are now interested for numerical methods. Okay. Hello. Suppose in our hand already we have unconstant optimization algorithm. The algorithm which is capable to find out minima or maxima of a given objective function only without checking the feasibility of the solution. Is it understood? Is it accepted?
Yes, sir.
Suppose instead of giving the objective function to the algorithm, we are modifying the objective function with this. This Pxr is the modified objective function, where R is a parameter called constraint multiplier. I will explain what is the role of R later. But suppose our modified objective function is a function of X and R. And it is given like this, the basic objective function fx. Fx is the objective function which is supposed to be minimized. Clear? Hello?
Yes, sir.
And now some additional terms are added to this objective function. And these additional terms are the function of the constraints. Function of the constraints. Look, Gx is the constant. Hx is the constant. And we have developed certain terms taking a function of constant, multiplying with R and added to fx. Okay? Hello? How the objective function is modified? It is the summation of the basic objective function and certain terms where those terms are function of the constraints. Function of the constraints. Is it clear? Suppose we can choose the function of the constraints in such a way that if constant is violated, they will generate positive terms. Am I clear, or my statement is clear or not?
Yes, sir.
The function of the constraint are of such nature that they will generate positive terms only if they are violating the constraint. Okay.
Yes, sir.
So what will happen? Suppose two solutions are compared. At one solution, the objective function is better, but the violation of constant is much. At another point, the objective function is not so good, but the violation of constant is good. Now, if our unconstant algorithm search the solution based on unconstant algorithm, it will only judge the value of objective function. But if we judge the modified objective function, which solution will be better to it?
So when the violation is within limit.
Why not? Why? Because fx is also there. Contribution of fx is also there. It is not leaving or it is not ignoring the value of fx, because in the modified objective function fx is very much present. But
Yes, sir.
additional terms are there which are more in case of violation.
Yes, sir. So whenever the violation is less, so we will get a better PXR because the violation will not affect the fx.
No, but our value of modified objective function is contributed by fx also. If the fx is too bad,
Okay. Yes, sir. Then it will be a problem.
so can I say a statement that if unconstant algorithm finds the better solution based on the modified objective function, it will put priority on both? Do you accept this statement or not? If it use the modified objective function, instead of prioritizing only objective function, it will put priority on both. It will judge the quality based on both, how feasible it is and how minima it is.
Yes, sir.
Everybody? All of you have understood the concept or not?
Yes, sir.
So these function of constants in the right terms are called penalty function, because it penalizes the objective function or it penalizes the solution if there is a violation in the constant, isn't?
Yes, sir.
So we have to identify appropriate penalty function for constants, because in case of unequal to constant, it is very difficult, because if it exceeds the boundary, then solution is violated. But it is one-sided, either greater than equal to 0 or less than. But in case of constant, either left or right, it can violate the constant in both ways, isn't? If hx is equal to 0 is the requirement, being hx greater than equal to 0, it is also violation, or hx less than equal to 0, it is also violation. In both the cases, the solution should be penalized. Am I right or not?
Yes, sir.
Whether hx is positive, whether hx is negative, in both the cases, it should generate positive term. Am I right or not?
Yes, sir.
But in case of unequal to type constant, suppose gx greater than equal to 0, so only when gx less than 0, it should penalize. Have you understood? So here I have explained the method with an assumption that we are starting with an infeasible solution and gradually improves the feasibility. Am I right?
Yes,
When
sir.
I am assuming that algorithm should be such that it will penalize the infeasible points and increase the value of objective function, so that there will be a resistance against the algorithm to be selected as better point. Because if the search algorithm is based on minima, searching minima, then if the value of objective function is increased, it will not be selected by the algorithm. So giving positive value in the objective function or contributing positive value in the objective function means penalizing. Have you understood the word penalty or penalizing?
Yes, sir.
So at what points there will be penalty in this case? When the point is infeasible. And what will be the amount of penalty? It should be depending on the degree of feasibility. Degree of infeasibility rather. Higher the infeasibility, higher the penalty. Am I right?
Yes, sir.
So that our unconstant algorithm will accept a solution as better if the violation is less.
Yes, sir.
Have you understood this method or not? This is called penalty function method. And when we are starting with an infeasible solution and gradually improve the infeasibility, or rather gradually improve the feasibility, then it is called exterior method, because our feasible zone is a closed zone, isn't in the design variable space. And infeasible solution lies outside that closed area. So we are coming from outside, moving towards inside. This is called exterior method. Have you understood this point or not? We are coming from, or we are rather dragging the solution from infeasibility zone to feasibility zone. Is it clear?
Yes, sir.
So in this case, the difficulty or defect in the solution was that it was not satisfying the constant. So infeasibility was the lacuna of the solution, and we have improved the feasibility This is exterior method. But can you imagine that sometime your solution, initial solution, can be such that it is well feasible, it is well within the feasible domain. If a solution is chosen initially and found to be satisfying all the constraints with a well margin, will you accept the solution or not?
Yes, sir.
Why yes? Will you not check for the minimization of the objective function? It may happen that solution is well feasible, but it is not good for minimizing or maximizing of the objective function, isn't?
Yes, sir, that may happen. In that case, we will reject that solution.
There may be another feasible solution where the degree of feasibility is certainly slightly less, but it gives a better value of objective function. Should we accept that solution or not?
Yes, sir, we should accept the solution with properly penalizing it.
So in case of starting with a feasible solution, what is the lacuna? That it is not good regarding objective function, isn't?
Yes, sir.
The target of the algorithm should be that better you lose some feasibility, because feasibility margin is well, it is well within the boundary. Drag the solution towards the boundary, make it feasible, but the margin of feasibility can be reduced because we will gain in objective function. So whether this approach is correct or not. So there the challenge against the algorithm is that margin of feasibility is more than the requirement. Rather, you drag the solution towards boundary. That means to reduce the margin of feasibility and improve in the objective function. Is my point understood or not? Hello? Shall I repeat? Hello?
No, sir, understood.
So can you suggest that in that case, where the objective function, where the solution should be penalized, at feasible point or infeasible point?
In the infeasible points, sir.
Why? Because our target is to reduce the margin of feasibility, not to improve the feasibility. In case of exterior method, our target was to improve the feasibility, as because it is very much infeasible, we should improve the feasibility. But here the situation is reverse. Here the margin of feasibility is more than the requirement, but we have to sacrifice in the objective function. So we like to improve the value of objective function and to reduce the margin of feasibility. So here penalty should be at feasible points, isn't? So that in the next step, amount of feasibility will be reduced. If you penalize at infeasible point, next step you will get a better feasible point. But if you penalize at a feasible point, next step you will get a point with lesser feasibility. And this is now our target, that we have to reduce margin of feasibility and improve in objective function. Am I right or not? So again, you tell, in case of we are starting with an initial solution which is very much feasible. Very much feasible means it is well within the feasible domain, away from the boundary, inside. So here the lacuna is that objective function is not so good. Feasibility is not a problem, because there is some redundancy in the feasibility. We can rather reduce some margin of feasibility. So here, what should be the approach in the algorithm? To penalize a feasible point or to penalize an infeasible point? It is clear? So again, penalty terms, this method is called, or this approach is called interior penalty function method. The previous one was exterior, because we started with an infeasible solution. We are improving the feasibility at the cost of sacrifice in objective function. That method was called exterior method. In this case, we are starting with an initial solution which is very much feasible. The amount of feasibility is more than the requirement. And here we are losing in objective function. So in the algorithm, there should be approach to improve the objective function by reducing the feasibility. So it has to penalize a solution which is more feasible, Am I right or not? দেখো এই জায়গাটা প্রশ্ন করে ক্লিয়ার করে নাও। Interior penalty function method, exterior penalty function method. In case of exterior penalty function method, starting solution is infeasible. Lacuna in the solution or limitation or defect in the solution to be accepted as optimal solution is that it is infeasible. So what is the task of the algorithm? To improve the feasibility. How? It should penalize the solution because of its infeasibility. What will be the benefit? In the next step, it will get a better solution in reference to feasibility point of view. And gradually it will improve, and ultimately we will achieve at a solution where the feasibility is within our desired satisfaction, or infeasibility rather is our within desired satisfaction. This is called exterior method. And in the algorithm, penalty function should be such that if the point is infeasible, it will contribute positive term. It will contribute positive term in case of searching minima and negative term in case of searching maxima, which is called penalization. Am I right or not? But in the other method, which is called interior penalty function method, their starting solution is feasible. Not only feasible, amount of feasibility is more than the requirement. You try to visualize the feasible space. It is a closed space, isn't closed space formed by the boundary line representing constant. Can you visualize? And solution is well within the boundary, well within the boundary. Rather, now our task will be to drag the solution towards the boundary so that the amount of feasibility can be reduced. But reducing feasibility, it is, I am not meaning that you will introduce infeasibility. Amount of feasibility will be reduced. Suppose your requirement is gx should be greater than equal to 5 and your solution is giving gx is equal to 10. So amount of feasibility here 10 minus 5, 5. But if you take the solution instead of 10, if you take 7, still it is feasible. But difference between 7 minus 5 is of course less than the 10 minus 5. So amount of feasibility is reduced, though it's still feasible. But if reducing the feasibility, keeping within the feasibility, if we improve in the objective function, shall we accept this or not? Hello?
Yes, sir.
So this is the task of the interior penalty function method. In case of interior penalty function method, the starting solution is feasible. Margin of feasibility is more than the requirement. Task in the algorithm should be to reduce the amount of feasibility and to get an improved objective function value. So penalty should be on the points where feasibility is more. Clear or not? Hello? When you are developing your constant equations or inequations, those have already taken care of the factor of safety. Even if your solution is at the boundary point of the feasible space, still it is maintaining the factor of safety, as because factor of safety is already included within the equation or inequation, isn't? Any question? Can I move? So look, there are certain penalty functions I will discuss. Now you have already understood what is meant by interior penalty function, exterior penalty function, and what should be the approach. Suppose parabolic penalty. Hx is the constant, okay? And penalty function is hx whole square. If hx equal to 0 is the constant, instead of that, at a point where hx is greater than 0 or less than 0, in both the cases it is violation. Do you accept or not? And in both the cases, hx whole square will be always positive term. Acceptable? So it is penalizing the infeasible points for equal to type constants. Is it acceptable or not? Hx whole square is a specific penalty function which is applicable for equal to constraint and for exterior penalty function, penalty approach. Why for exterior? Because it is penalizing in case of infeasible point. Why it is for equal to constant? Because it penalizes whether hx greater than 0 or hx less than 0. Am I right? Hello? Next, infinite barrier penalty term. Here look the shape of the function. It is just the magnitude of the, so it will be always positive term. It is also used for unequal to type constants, and infeasible points are penalized. Log penalty. You know that in case of gx less than equal to 0, what will be the value of log gx, ln gx? Suppose gx greater than equal to 0 is the constant, okay? So not give any value because ln of negative value is meaningless. Hello.
Yes, sir.
So it will not penalize infeasible point. It will penalize only feasible points. Do you agree or not?
Yes, sir.
So for which method it is applicable?
So interior penalty.
Very good. So I think you can go through several penalty functions are there. You can design, you can suggest new penalty function. If you understand the concept of interior method, exterior method, purpose of putting penalty terms in the method, depending on your interior or exterior approach, you can select appropriate penalty terms for equal to type constants and unequal to type constants. Is it understood or not? Hello? Okay, now I am going to discuss the role of R. Look, from the beginning, the penalty functions are multiplied by the parameter R, and the R is called penalty multiplier. Okay. Suppose R is 1. With this, we run the program and we get a solution. Ultimately, in case of penalty function method, we cannot eliminate the infeasibility. Suppose if it is exterior method, we cannot eliminate the infeasibility completely, but we can reduce it, isn't it? Hello? Hello?
Yes.
So with R value 1, penalty terms are contributed directly by the penalty function. But suppose if we make, after getting the optimum solution with R is equal to 1, then again in the next run, we make R is equal to 10 and run the same program. What will happen? In every iteration, the penalty value will be magnified by 10 times. Isn't? So ultimately, the priority of satisfying constraint will be more in the algorithm because the R value is 10. It is always magnifying the infeasibility. Do you agree or not? So making R is equal to 10, at the end, we will arrive at a solution where surely the satisfaction of feasibility will be much better than the previous one. But of course, we may have to sacrifice in objective function. Do you agree or not? R will control the priority of satisfaction of constraint level in the algorithm. Weightage. Because in the modified penalty function, both minimization and constraint satisfaction are important. Both are important. But what will be the weightage of importance that can be controlled by the value of R? If R is equal to 1, they are equal important. But if I make R is equal to 10, then probably we are putting priority, increasing priority of the constraint satisfaction. If we make R is equal to 0.1, rather we are reducing it. So by controlling the value of R, we can rather increase or decrease the priority of satisfaction of constraint level. Accepted or not?
Yes, sir.
So R is called penalty multiplier. Okay, I require one suggestion, or rather, what is your opinion? That when it is exterior method, the point is infeasible, what will be our urge? To increase the priority of satisfaction level of constraint or not?
Yes, sir.
Yes. But when we are using interior method, initially we are well away from the boundary line. We can start with a R value of standard value or higher value, but gradually when we are moving towards boundary, what should be our precaution? Should we increase the penalty, or we should be very cautious that we may exceed the boundary? Rather, now we should put, or rather reduce the weightage of penalty.
So
What is your opinion?
we should reduce very slowly.
So if I now give a statement that in case of exterior method, R starts with a small value but gradually increases to very high value to increase the desired of feasibility, or rather important normal R value, but gradually we have to reduce the R value to reduce the penalization, because otherwise we may exceed the boundary. We can exceed the feasibility criteria at all. We are starting with a very well margin of feasibility, but we are now crossing the limit and exceeding the feasibility criteria. That is not acceptable. So R should be reduced. At the boundary, at the very close to boundary, it should be very low value. Penalization should be very low. Do you agree with me or not?
Yes, sir.
So in case of interior method, R should be reduced gradually instead. Am I right?
Yes, sir.
So here one example has been given for your explanation. Look, if you follow the table, when the R value is 0.1, okay, look, constraint violation is in the order of this value. But when your R value is 1, the constant, the violation order is gradually reduced and gradually reduced. When 10, further reduction. These are the optimum solution after convergence. Okay. Now, okay, this is my last presentation. You are a designer. You have to satisfy the constraints, and also you have to minimize or maximize the given objective function to get an optimum solution. But optimal solution, it will be very rather difficult for him to choose because there is no option. Rather, he will be happy if he gets scope to get multiple solution, multiple optimum solution, and among them he can choose according to his requirement, isn't?
Yes, sir.
So look here, we have got optimal solution for different value of R. For different value of R, the blue point represents the value of the objective function, and the orange color point represents the amount of violation. Okay, for R is equal to 1, and your problem is to get the minimum value of some objective function. So look, for R is equal to 1, your solution represents the value of objective function and value of constant. And what is the observation? That constant violation is very high, but the objective function is the best, very low. Am I right?
Yes, sir.
Now, if you make R is equal to 1, you will improve in the constant violation. Look, all these solutions are the final optimal solution. Final optimal solution for a given value of R. All of those are optimal solutions, but for different value of R. So the second solution is better in respect to constant satisfaction, but worse in respect to objective function. Do you agree
Yes,
or
sir.
not? This thing will continue for increasing R. So designer has provided 10 or 20 different solutions for different R. And all the scenarios are given to the customer. Okay? Hello?
Yes, sir.
Now, how customer will choose from this solution? Now, customer has to decide what maximum constant violation it can allow. It has been given in the constant list that Hx should be equal to 0. But he knows, though it is theoretically given Hx should be 0, but if Hx is equal to 2, it will not create problem. This is the acceptable constant violation, 2. So thus, to the customer or to the designer even, there are certain hints about permissible constant violation. Am I right? Is my statement clear?
Yes, sir.
Now he will put a horizontal line based on the permissible constant violation. Suppose if your limit is the upper line, limit 1 for constant violation, then you cannot go beyond this level. Your constant violation cannot go beyond line. Clear?
This is the permissible limit.
Permissible constant violation limit. Amount of constant violation that limit. Now can you suggest if your constant violation limit is limit 1, which solution is the optimal, final optimum solution?
So R equal to 10.
Very good. Is it from your clear conception?
Yes, sir.
Now somebody finds that no, such amount of constant violation will be risky. Rather, only up to, we can violate up to limit 2, which is less. Then what will be the optimal solution?
1000.
But somebody can argue, in the second case, your objective function value is deteriorated.
Yes, sir.
So how I can accept it? What will be your logic as designer? You still argue that it is the optimum solution. Then you will argue that optimal solution means the best solution for a given condition. If your condition changes, your optimal solution will change. It will not be based on only the value of objective function. Other conditions are to be satisfied. So while getting or searching for optimal solution, somebody should not concentrate only on the objective function and cannot argue that the objective function is deteriorated, so how it can be optimal. It can be optimal even at the deterioration of objective function if it is optimal, satisfying all the given criteria. In case of other solution, your constant valuation condition is not satisfied. Am I clear?
Yes, sir.
So this is the designer's role. This is the designer's role to provide a solution space of optimum solution, to provide a solution space of optimum solutions, among which or from which the customer will be comfortable to select according to his restriction or given. Is my point understood or not?
Yes, sir.
No. বলো অনন্য বুঝেছো পুরোটা না কোনো কোয়েশ্চেন আছে? শুভম?
Yes, sir. বুঝেছি।
বিপ্লব,
ইয়েস স্যার ঠিক আছে
অর্কপ্রভ,
হ্যাঁ স্যার বুঝেছি স্যার।
দীপাঞ্জন,
ইয়েস স্যার
মোহন,
ইয়েস স্যার, বুঝেছি স্যার।
অনন্যা,
হ্যাঁ স্যার, বুঝতে পেরেছি।
আর কে আছো? অরিজিৎ চলে গেছো নাকি?
না স্যার, ওই কানেক্টিভিটির গন্ডগোল হচ্ছিল একবার, মাঝখান থেকে বেরিয়ে গেছে।
রহিনা?
হ্যাঁ স্যার, বুঝেছি।
আচ্ছা, শুভম তো আগেই বলছো। তোমাদের আর কোয়েশ্চেন নেই তো কিছু? দেখো, আন্ডারস্ট্যান্ডিংটা ইম্পর্টেন্ট। এরপরে বই পড়লে বা যে কোনো অ্যালগরিদম দেখলে সেখানে না বোঝার কিছু নেই, কিন্তু এই কনসেপ্টটা যদি বুঝে নিতে পারো, কনস্ট্যান্টের সাথে আনকনস্ট্যান্টের তফাৎ, অ্যালগরিদমে কি এফেক্ট করবে। এবার আমার সার্চিং অ্যাপ্রোচটা যদি এক্সটেরিয়ার হয়, তাহলে তার সার্চ টার্গেটটা কি থাকে, অ্যালগরিদমের টাস্ক কি হবে, এক্সটেরিয়ার হলে কি হবে, আর পেনাল্টি আলটিমেটলি আমরা কোথায় গিয়ে পৌঁছবো, এটা যদি বুঝে থাকো, পরেরটা বুঝে যাওয়া উচিত আর কি। দেখ, কোনো কোয়েশ্চেন আছে কারণ? নেই তো?
স্যার বলছি আপনি যে স্যার গ্রাফটা দেখালেন লাস্টে,
হ্যাঁ
সেখানে স্যার পারমিসিবল কনস্ট্যান্ট ভ্যারিয়েশনের দুখানা হরিজন্টাল লাইন ছিল।
হ্যাঁ
মানে প্রবলেমে যে মানে অ্যাকচুয়ালি যে সলিউশনগুলো বার করা হয়েছে অপটিমাল সলিউশনগুলো,
হ্যাঁ।
সেগুলো যে কনস্ট্যান্ট মানে ছিল আর কি, কনস্ট্যান্টগুলো সেগুলো কি মানে মানে পারমিসিবল থেকে আরো কম ছিল মানে লিমিটটা থেকে?
না না, আমরা দেখো আমাদের প্রবলেমটা দেওয়া ছিল যে এইচ এক্স শুড বি 0, কিন্তু আমরা যখন ওই পেনাল্টি ফাংশন মেথডে আমরা তো কমাতে কমাতে গেছি। এইচ এক্স প্রথমে 0-র পরিবর্তে এসছে 25, নেক্সট ইটারেশনে 22, এই করতে 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 যখন কনভার্জেন্স হয়েছে তখন দেখা গেছে ওইটা হয়তো 3 হয়ে আছে। ওটাই অপটিমাল সলিউশন উইথ কনস্ট্যান্ট ভায়োলেশন 3। ওই জন্য দেখো প্রত্যেকটা অপটিমাম সলিউশনে আমি যে প্লটটা দিয়েছি, অরেঞ্জ কালারটা রিপ্রেজেন্ট করছে ওই অপটিমাল পয়েন্টে অ্যামাউন্ট অফ কনস্ট্যান্ট ভায়োলেশন কত হয়েছে। প্রত্যেকটাতে কনস্ট্যান্ট ভায়োলেশন আছে, কিন্তু কমিয়ে একটা পার্টিকুলার জায়গায় গিয়ে আমি ওটাকে ছেড়ে দিয়েছি, আর এগোইনি, রেখে দিয়েছি। কিন্তু আর যত বাড়াবে তত কম ভায়োলেশন রেখে ও অপটিমাল সলিউশন দেবে।
আচ্ছা স্যার বুঝলাম স্যার।
মানে অরেঞ্জ কালারটা তুমি খেয়াল করে দেখো, প্রত্যেকটা অপটিমাল, আর 1 এর জন্য হোক, 10 এর জন্য, প্রত্যেকটা পয়েন্টে দেয়ার ইজ সাম অ্যামাউন্ট অফ কনস্ট্যান্ট ভায়োলেশন। আমি অ্যাপ্রোচটা করেছি ফিজিবিলিটির দিকে যাব বলে, কিন্তু সবকটাকে ফিজিবিলিটিতে নিয়ে পৌঁছতে নাও পারি। কনভার্জেন্স লজিকটা দেওয়ার উপর ডিপেন্ড করছে যে একটা সার্টেন টাইমের পর আমাকে থামতে হবে। যখন থামছি অপটিমাল সলিউশন বলে, তখন যে অ্যামাউন্টের কনস্ট্যান্ট ভায়োলেশন থাকছে সেটা থাকছে। কিন্তু আমি বলছি এই যে কতটা কনস্ট্যান্ট ভায়োলেশন রেখে ও অপটিমাল সলিউশনে কনভার্জ করবে, সেটা ডিপেন্ড করছে আর এর ভ্যালুর।
ওকে স্যার।
এনি কোয়েশ্চেন ফ্রম এনিবডি? এই অবধি আমাদের ক্লাসের মানে টপিকের একটা পার্ট হলো, মানে আমাদের যদি 3টে পার্টে আমরা ভাগ করি, তার মধ্যে এটা ফার্স্ট পার্ট হচ্ছে ট্র্যাডিশনাল মেথডস আপ টু কনস্ট্যান্ট অপারেশন প্রবলেম। তার মানে এইটা একটা কিন্তু কমপ্লিট কোর্স হলো। তোমাকে যদি একটা কোনো ডিজাইন প্রবলেম দিয়ে বলা হয় যে তুমি এর কনস্ট্যান্ট অপটিমাম সলিউশন বের করে দাও, তাহলে তুমি কিন্তু তোমার করা উচিত ইউজিং অল ট্র্যাডিশনাল মেথডস। তুমি ধরা যাক পেনাল্টি ফাংশন মেথড চুজ করলে, তার ভেতরে তুমি আনকনস্ট্যান্ট অ্যালগরিদম হিসেবে কচি স্টিপেস্ট সিলেক্ট করলে, কচি স্টিপেস্টের ভেতরে, কচি স্টিপেস্টটা মাল্টি ভেরিয়েবল, তার ভেতরে তোমার সিঙ্গেল ভেরিয়েবল হিসেবে আলফাটাকে অপটিমাইজ করার জন্য গোল্ডেন সেকশন সিলেক্ট করলে। বলে একটা সিঙ্গেল ভেরিয়েবল, একটা মাল্টি ভেরিয়েবল এবং আনকনস্ট্যান্টের অ্যাপ্রোচ, এইটা দিয়ে তুমি কিন্তু একটা অ্যালগরিদম বা একটা প্রোগ্রাম লিখতেই পারো যেখানে কনস্ট্যান্ট অপটিমাইজেশন প্রবলেমকে সলভ করতে পারবে। এগ্রি করো? এবার বলো, আমরা কি একটা অ্যাসাইনমেন্ট নিতে পারি যে একটা কনস্ট্যান্ট কমপ্লিট কনস্ট্যান্ট অপটিমাইজেশন প্রবলেমের জন্য একটা প্রোগ্রাম লেখা বা অ্যালগরিদম বানানো করতে পারো? কিন্তু তাকে ম্যাটল্যাব শিখতে হবে আমি বলবো না। তুমি যদি অন্য ল্যাঙ্গুয়েজে কমফোর্টেবল থাকো, অ্যালগরিদম তুমি বানিয়ে আমাকে রেজাল্ট দেখাতে পারলেই হবে। আমরা কি অ্যাসাইনমেন্ট নেব? এটার সাথে পরীক্ষার কোনো আপাতত সম্পর্ক নেই, কিন্তু তোমরা যদি রাজি থাকো আমি এটা অ্যাসাইনমেন্টটাকে একটা বাফার হিসেবে রাখতে পারি। যাদের ক্ষেত্রে ক্লাস টেস্ট খারাপ হবে তাদের ক্ষেত্রে অন্তত দুটোর মধ্যে যেটা বেটার হবে সেটা নেওয়া যেতে পারে। তোমরা যদি এগ্রি করো যে অ্যাসাইনমেন্টটা করে রাখুন, আপনি অ্যাসাইনমেন্ট ইভ্যালুয়েট করে রাখুন। আর যদি ক্লাস টেস্ট খারাপ হয়, তার মানে দুটো ক্লাস টেস্ট আর একটা অ্যাসাইনমেন্ট বা একাধিক অ্যাসাইনমেন্টের একটা মার্কস ইভ্যালুয়েট হতে পারে। 3টের মধ্যে বেস্ট 2 দিয়ে করবো, সেটা তোমরা যদি রাজি থাকো তাহলে সেক্ষেত্রে আমি করতে পারি। বা তোমরা যদি এই ইভ্যালুয়েশনের সাথে না জড়িয়ে তোমরা যদি বলো আমরা খানিকটা ভলান্টারিলি বা ফ্রি স্টাইল থাকবো, আমার দিক থেকে রিকোয়েস্ট, একটা টার্গেট নাও। যারা প্রোগ্রামিং ভালোবাসো, লিখতে ভালো, কোডিং করতে ভালোবাসো, তারা একটা কোড তৈরি করো যেটার মধ্যে ওই কনস্ট্যান্ট মানে পেনাল্টি ফাংশন মেথড হবে, ভেতরে কচি স্টিপেস্ট, আর তার ভেতরে গোল্ডেন সেকশন। কে কে নেবে, অ্যাকসেপ্ট করবে বলো? এটা ভলান্টারি।
স্যার আমি চেষ্টা-
কে কে নিজে থেকে বলো, আই উইল বি হ্যাপি ইফ ইউ ভলান্টিয়ার ফ্রম ইউর সেলফ।
স্যার করে দেখবো।
আর ঠিক আছে, এটা হলেই হবে, ট্রাই করে দেখো। এটার সাথে পেনাল্টি, তোমাদের জন্য কোনো পেনাল্টি নেই এটাতে, অনলি অ্যাপ্রিসিয়েশন আছে। সো ইউ ক্যান ভলান্টিয়ার। ঠিক আছে,
ইয়েস স্যার।
তাহলে নেক্সট ক্লাস সোমবার থেকে যেটা করবো, মানে আমি এটা এই কারণে আজকে বলে শেষ করলাম, সোমবার থেকে কিন্তু আমরা নন ট্র্যাডিশনাল মেথডগুলোই যাব, যেগুলো একটু ডিফারেন্ট মেথড, একটু অন্য টাইপের মেথড, এটা একটু দেখে নিন। সো থ্যাংক ইউ অল। ওকে,
থ্যাংক ইউ স্যার।
ওকে।
থ্যাংক ইউ স্যার।